Okay, so we can start. So I have uploaded in Beep the text of this exam. It's called simply with the name is with the date of today, and currently you have only the text, not the solutions. But then I will also upload the solutions after today. Okay, so I think the best is to keep the text on the projector, so I don't have to draw everything again. And I will use the Blackboard to solve for the solutions. I cannot make a video recording because we are using the Blackboard, and unfortunately video recording doesn't work if I use the Surface, because it doesn't work with the pen. So I will make an audio recording. Maybe do the same. Okay, so let's start. This is an example of an exam, and it is composed of four parts, five parts, as you can see. There are 4 exercises with text and some numbers that you have to solve, and then a set of questions. Usually there are 3 questions. There are 3 questions, it can be 3 or 4, and questions must be answered in writing a very short part, so that you don't have to explain lengthy concepts. And so we will go through it, and I hope we will make it on time. I will not solve every detail, because otherwise it takes a little bit too much, but we'll try to get most of it. But there is no chalk. Can somebody go upstairs to take chalks, please? See, so this is particularly it's not easy as classwork, and I can say that it's more difficult than the average text. So we can it's just for practice, but it's a little bit long. And I think that in the real exam you will have 2 hours to solve the text, roughly 2 hours. So while we are waiting, I can start reading the first exercise, which is quite simple. It's a network with 3 routers, and we have thank you. You have a set of destinations, and the text says that in R1 you have 6 packets to be transmitted, and the packets are in sequence A, B, B, C, C, where these letters represents the destinations of the destination of each packet. So the text says that at time t equal to 0, the output Q has 6 packets towards the destinations, and the channel is available. Assuming that the length of the packet is 500 bits, this is common to all the packets. We have to find, to calculate the instant in which each packet arrived to the destination. So first of all, we can start calculating the transmission times of all the network. So we have transmission time. Here the channels links are identified by numbers. So as you know, the transmission time on the generic link is given by the length of the packet, which is common to all the packet, divided by the capacity of the link. Okay. So now we have T1, which is the transmission time of a packet over the link from R1 to R3. T1 is 500 bits divided by 250 kilobits per second. This means that you have the kilos downstairs, so it becomes a millisecond, and this is 2 milliseconds. Okay. And now you can easily calculate immediately all the other times, because, for example, on the link 2, the capacity is double as well as on link 3, so it means that the transmission time will be half. And then on link 4, the capacity is 1/4, so it means that sorry, it's the half of the original, so it means that the transmission time will be 2 times. And on link 5, the capacity is 4 times the C1, 250 by 4, and therefore the transmission time will be 1/4. Okay, so it's 0.5 milliseconds. Okay. Now we have to look at the packets and the path followed by each packet. Here the text is a little bit misleading because it says at output queue of R1 there are 6 packets that are going to the destination, but if you remember, when you have 2 different links, each link has his own output queue. Okay? So basically all the packets that are going towards R3 are hosted in a queue in R1. The packets that are going towards R2 are hosted in another queue. Okay? So we can start with packets that are going towards R3, packets going to A and C, because here the topology is very simple. You have a single path for all destinations. So let's start considering packets that are going towards, for example, A. This is R1. And here we represent the buffer that is in the output queue of the link towards R3. And here we will have R3, A, and A, because packets that are going to A, we have to cross R3 and then go towards A. Okay. So there is no indication that we are using cut through, so we can assume that everything is store and forward, means that the intermediate node will not transmit the packet until it has received it completely. And so you can start drawing the two packets in R1 that are waiting to go towards A, destination A. So then you have the propagation time on the link R1, R3. Then when each packet is arriving to R3, it is retransmitted, and the retransmission speed is faster. So the T3, T sub 3 is the half of T sub 1. This means that in this queue, you don't have queuing. As packets arrive, they are immediately transmitted, and the second packet does not wait into the R3 queue. Okay? And then there is another propagation time, and then the packet arrives to A. And for example, if you want to calculate the time of the arrival of the second packet to destination, this will be easily calculated by using the technique that I have mentioned. If you want, it's a graphical technique. You start from the end point of the interval, and you go up each time you can, and then you go horizontal. Each time you can go horizontal. So in this case, you go up here, horizontal here, up again, and then horizontal for these two packets. Okay. So the arrival time will be tau 3. This is link number 3. This is link number 1. Tau 3 plus T3 plus tau 1 plus 2 times T1. Okay. And if my calculations are correct, it should sum to 6.5 milliseconds. Okay. So now we can consider packets that are going towards C. Okay. And these packets will wait in the queue from R1 to R3 because they have to go through R3 as well. So they can be transmitted. I can use the same graphic in the first line. So they will be transmitted only after packets that are going to A are completely transmitted. But now we have to change the path. So in order to be clear, you should draw another graph, but here, in order to be short, I will only delete something. This is link number 4. So these packets, I can delete these packets because when they arrive, when the packets that are going to C arrive in R3, they will be forwarded through a different queue. Okay, so they are independent of the packets that were sent to A. So the packets arrive to C after a propagation time. And then in C they are transmitted on link number 4. If you look at T4, it's longer than T1. So it means that the second packet will have to wait in the queue. Okay, so the first packet starts being transmitted, and then after a time that is equal to T4, also the second packet will be sent to C. And they propagate towards C. Okay. So this time, when we are reconstructing, for example, the sequence of events to calculate the arrival time of the second packet in C, now we have to sum these components. First we have a tau 4, which is propagation delay on the last link. Then we have to count all this time. It is the waiting time in tau in R3 plus transmission time. Then you go up, and then this is the last component. So in total, when you are summing these components, we have tau 4 plus 2 times T4 plus tau 1, and then we have 3 times T1. Which should sum up to 16 milliseconds. Okay. Okay. Then finally, now we have the 2 packets that are going towards B. They are transmitted immediately because they go into another queue, so they don't have to wait for the packets for A and C. They can be transmitted in parallel, and they will be transmitted and on the interface towards link number 2, and then they will arrive at R2. So they are transmitted on the output queue from R1 to R2, and then from R2 they are going to B. And in order to go to B, they cross link number 5. Okay. So we can start from t equal to 0. The transmission time in this case is 1 millisecond. Then we have propagation time. And then in R2 they are retransmitted on link number 5. And here the transmission time is 0.5 milliseconds. So it's shorter than the previous transmission time. So again they are transmitted. The second one is transmitted immediately. It is not waiting in the queue in R2. Okay. So in a similar way as in the previous case, if we want to calculate the arrival time of the second packet, here we will have tau 5 plus T5 plus tau 2 plus 2 times T2. Okay. Should be 7.5 milliseconds. Okay. So this exercise was relatively easy. And questions? So we can go to the second one. See if I can find also that. This I need. Okay. So this is the second one. It's about IP addressing. And so it says that we have a small internet service provider which is assigned a block in the IP addressing space, which is defined by the numbers 169 dots 147 dots 140.0, and the net mask is 255.252.0. Okay. So from the net mask you can immediately calculate the length of the prefix, which is slash 22. Okay. Because 252 is in binary numbers 1 0 0. Okay. So this here would be 24, 23, 22. If you want to do it fast, this is 255 minus 3. Okay, that means helps in the conversion. Okay, so this is the network address, and we have this map that represents the physical infrastructure, and here you can see that there is the connection towards the internet with this router 1, and then there are other components, the routers, other routers, which are represented by this graph, and switches and Wi-Fi access points. Wi-Fi access points are equivalent to layer 2 switches. Okay, so you can think about them as simple layer 2 switches. The first action to do is to partition this network in order to understand how many IP nets we have, if we want, of course, to follow the common practice of assigning an IP net basically corresponding to each broadcast domain, layer 2 broadcast domain. Okay, and so here we have 3 networks that are already identified. They are represented by these clouds, and then we have an indication that says that for each of these switches we have 26 ports. Okay, so each switch that is connected to hosts has 26 ports. So it means that, for example, in this case, you have 25 hosts connected down here, and then 1 port that is used to connect to the router. And the same for this switch, and so on. Okay. Then we have a Wi-Fi network and then we have some point-to-point links. And now we need to know what is the requirement in terms of number of hosts of each network. And for the first three networks, the requirement is explicitly mentioned in the text. It says that client network 1 and 2, these two, needs 250 addresses each. Client network 3 needs 100 addresses. And then we have that each switch is connected to hosts has 26 ports. And then here, for the wireless network, obviously being Wi-Fi, we don't know a priori how many hosts are connected because this is variable number. But the text says that the DHCP server needs a pool of 100 addresses. Okay, so it's configured to manage a pool, to assign a pool of 100 addresses. So practically it means that this network will require 100 addresses. Okay. So now we have to identify the networks, and the rule is always that you should assign an IPNet to each layer 2 broadcast domains. This means that each time you have a router, as you know, each interface of the router will must be on a different IPNet. Okay, and this is always helpful when you want to identify the networks in these kind of pictures. So, for example, if you have this router R2, you see that it has 3 interfaces. You immediately know that PP1, that is the point-to-point link, will be one network, one IPNet, and then you will have another IPNet, which includes this switch and the attached hosts, and another IPNet, which include the second switch and the attached hosts. They must be on a different IPNet, because they are connected to the switch through different interfaces. Instead, if you look here in the center, you have a set of switches that are connected by trunk ports, like for example this switch connected to this and so on. And the whole layer 2 network that is made of interconnected switches is connected to R1 and connected to R2. And so you will have one interface that is connected to this network on R1, another interface on R2. But there are no routers inside. So the whole set of switches is a single IPNet. Okay. So once we have this clear, this is the partition that you can obtain. I don't draw it again because it takes too long. So here you have the first one network here that is connected to R1 and R3. Obviously, an IPNet can be connected to several routers, so not always a single one. Then you have here in R2 these two networks that are separated. R5, you have a single network connected. R6, these are already identified. R4 is connected to the Wi-Fi network, and the Wi-Fi network is composed by a set of access points that are equivalent to the switches, and then a central switch. And you have a single interface towards the router. So this is a single whole network. Okay. Once we have identified the IPNets, we have to consider what is the requirement of each IPNet in terms of hosts, and so in terms of number of addresses that are required. Always take into account that whenever you have an IPNet, you need one address to identify the network, which is the one with the host address all equal to 0. And you need the limited broadcast address, which is the one with the host ID all to 1. Sorry, not the directed broadcast address. So you have two addresses that are reserved, and then also you have to take into account that sometimes you not only have to count the number of hosts, but also to consider the interfaces of the routers. Each interface consumes one address in that pool. Okay. So, saying that, we can start identifying the requirements in terms of number of addresses. So here we have 26 ports. 26 ports, they are used to interconnect 25 hosts and a router. So in the total we have 26 hosts. Okay. This is the requirement in terms of number of addresses that are assignable to hosts. Then you have to consider a +2 because there are two addresses that are reserved. The same for this network. Here the text already says that you need the 100 addresses for the whole network, maybe +1 if you want to consider the interface of the router. These are already assigned, 250, 250 and 100. Then you have this network that is again the same of this case here. And then what about this network on the top? Here we have 25 hosts here because this router has 26 ports. So one is used for the trunk port connecting to the this switch. One is used for the trunk port connecting to the other switch. The remaining 25 are used to interconnect the stations. So here we have 25 hosts, 25 here, 25 here. In the total we have 75 hosts. And plus you have to consider that here you need another interface, so it would be 76 actually, in terms of requirement. I wrote 77. So once we have written the requirements in terms of number of addresses for all the networks, then we can start thinking about the size of the address blocks that are assigned to each IPNet. And as usual, you have to consider the smallest integer power of 2 that is containing the number of addresses that are required. So for example, here if we have 100 addresses requested, then we need at least 128 addresses in the block. Okay, because 128 is the smallest integer power of 2. So 128 means 2 to the 7. Okay. So if we want to now define what is the extension of the net mask, of the subnet mask of this network, we just need to take 20, the extension would be 32 minus 7, because we need 7, at least 7 bits for the host ID. Okay. Now, since we want to be always conservative, the rule is always that you have to assign to the network the smallest number of the smallest number of addresses, so the smallest block possible, so that you can have extra addresses for future expansions. Okay. Here, in this case, the minimum number is 128, so it means 2 to the 7, so it means /32 minus 7, that is /25. Okay. So this network will be this subnet will be a /25. Okay. Then in this case we have 250 addresses required. So if we do it as /24, it means that the block will have 255 addresses. That is okay. And the same also for network number 2. Here we have again 100 addresses required, so it will be a /25. And also in this case, since we have 77, will be a /25, okay? Because if we want to consider the smaller, the first smaller network, it will be a 64. It contains 64 addresses, which is not enough. So we have to use a 128 block. So this would be also /25. Then here we have these networks that are smaller. They require 26 addresses each. 26 addresses means that you can provide it with a block of 32. That means 2 to the 9, okay? Sorry, to 5. So it means that these would be, they would be 27, okay? /27. And this is holds for network 8, 7, and 6. And finally, we have the point-to-point links. For the point-to-point links, we need 2 addresses that are assigned to the 2 interfaces of the routers. But then we have to consider the 2 addresses that are reserved in order to identify the network. So it means that each point-to-point link will need a block of 4 addresses, okay? Which means that it will be a /30, okay? So it's not written on the picture, but it's a /30 for all point-to-point links. So this is basically what we need to start subnetting, the subnetting operation. And here the text requires that we do the subnetting, first identifying the boundaries and assign letters for each subnet. Then we have to define the addresses, net mask, and direct broadcast address, and then write the routing table for router number R3 in the most compact way. So, let's start the subnetting operation. I write again the starting network address. This is the overall network address. Okay. Now the rule is that you have to start considering the largest subnets. And in this case, the largest subnets that we need are /25, okay? And also remember that when you are /24. When you are subnetting and you add a bit, each time you add a bit to the network prefix for the subnet extension, it means that you are halving the original address space. If you are adding 2 bits, you are dividing the original address space in four parts, and so on. So now we have to move from /22 to a /24, and therefore we will create 4 subnets. Okay, so the first one, I only write the addresses of the subnets. The address numerically is the same as before, but now is /24. Okay. And this one, for example, we can assign it to N1. Then we have another block, a don't copy everything, of course. And the second block is starting. So /24 means that we are using the whole third byte as part of the subnet address. So the next block will start with 141. Okay. And this is because when I am adding 1 here, it means that I am considering 255 addresses ahead compared to the starting address, which is this one. Okay, 256. So this is N2, and then we have another block. This block, we don't have networks, other networks that are /24. So this block, for now, we can leave it unused. And then we have the fourth block, which is this one. And again, we leave it untouched. Okay. So since we have satisfied all the networks /24, now we can go to the smaller networks, the next smallest, and the next smallest is the next smallest are the networks with /25. And here we have 3 networks that have to be /25, and 3 and 4 and 5. So we can start taking the first 2 from the first unused block. The first unused block becomes this point divided in 2. We are going from /24 to /25, so it means that we are increasing by 1 the number of bits in the network prefix. And therefore we generate 2 subnets. So one will be 142.0/25. We can assign it to N3. Okay. The second one. Now we are considering that the network prefix is including the first bit of the last byte. Okay. So the next block will start with the decimal address 128 in the last byte, /25, and we assign it to N4. Okay. So now we have still another /25 plus smaller networks. So I start from this block. So far we have assigned everything. I start from this block, which is the last one available. And again, we move to /25, so we generate 2 subnets. The first one will be 143.0/25. We can assign it to N5. And then we generate the second block in a similar way as before, which is this one. Okay. Now from this block we can start splitting it again, so we can assign it to the other networks. Now we have a certain number of networks that are /27. Here we have /25. If we add another 2 bits, we are splitting the block in 4 parts, which is what we need. So here we will have, I don't repeat 142, 128/27. and we can assign it to n6. Okay. Which is 4, 5, 6, this one. Then we have so now we are in the range of /27. So it means that each block is 32 addresses. So another way to understand where there is the beginning of the next block is to add 32 to this number. So the next block will start at 160. Then we have another block which is starting 32 addresses later, so 192. And finally, the last block is 192 plus 32, which is 224. Okay. But all the network, all the /27 networks have been assigned. So the last block, we have to use it in order to assign the point-to-point, the addresses to the point-to-point links. So I don't, so I have to continue here. Okay. So we can start with 224, and now we want the point-to-point links, so we can split, if you want, you can split it by using /30. This is the first point-to-point link. Since we are increasing by 3 bits, it means that we are adding, we are splitting the address block in 8 parts. So here we have 2 to 8. Then we have the 32. Point 3. Okay, this is the last one. So if you do this, it's correct as a solution, but you will also have the remaining part of the addresses that is in principle split into very small blocks. So you may adopt an alternative. For example, you can split this block by doing first an extension of only, for example, 1 bit. So you will have /26, 2/20, you can generate 2/26, and then you can use one of the 2/26 to generate the 28. Then you can use one of the 2/28, generate the 4/30, And so the other part is /28 that you can use for future purposes. Okay, but it's practically the same. Okay, so this is basically the result. I have only written the addresses of the networks. I don't write also the addresses of the broadcast address, but it's very simple. For example, in this case, if you want the broadcast address of this network, you just take the starting address of the next network and you subtract 1. Okay, so in this case it's very easy. It will be .255, but the same you can apply to all the other cases. So once you have defined the broadcast addresses, in order to answer to the second question, that is the routing table of router 2, you have also to assign explicit addresses to the router interfaces, because the router 2 is here, so it is connected to the router 1. No, sorry, the router 3. Router 3 is there. Is connected to router 5, router 6, and through this network here, is also connected to router 1. Okay, so router 1, 5, and 6 can be next hops for router 3. So when you are compiling the routing table of router 3, you will have to place in the column of the next hops the addresses of the neighbors, and so you have to assign an explicit IP address to the interfaces of R5, R6, and R1 towards R3. Okay. Then once you have done this, you have to look at the map of the network, and you have also to find what is the next stop going to each destination, and the destinations will be all the subnets of the network. For example, if you take N7, that is this subnet here, in the routing table, you will have to write, so we can do it for one case. Is destination, next stop. Okay. Now for short I will say that the address of R1 is A, the address of R5 is B, and the address of R6 is C. Okay. Then I also write the networks in a synthetic way, so you will have network 1, network 2, network 3. And now, for example, if you want to write the entry for network 1, it will be, the next stop will be R6, so C. Network 2 will be C again. Network 3 again C. Okay. Network 4 Where is it? So, this one. The same. And then you have network 5. We go through B. Sorry, network 6, we go to B. Network 5 is directly connected. Okay. So here, network 5, as you can see, is directly connected to one of the interfaces of R3. So you can list it in the routing table or separately, but it's important that you notice that it's directly connected. And for example, here you can write the interface of R3. Let's say that this is R3, which has 3 interfaces. Let's call it X, Y, and Z. X is towards R1. Z is towards R6. R5. R6. Okay. So here R5 is reachable towards interface X. This is the interface. Okay. And this is important because it's directly connected. R5 is directly connected to router 3. Then if you want to be very complete, you can also write down the interfaces for the indirect forwarding. For example, C is connected, is the interface of R6, and R3 is connected to R6 through interface Y. So here we will have to write Y. Okay. This is B, and 7 is there. So we go through R1. R1 is 8, and so forth. Okay. Now, once we have written all the table here, you will have to replace these numbers with IP addresses. You may notice that there are the possibilities to do route aggregation. For example, if you consider network 1 and network 2, network 1 is .140.0/24, and network 2 is 141.0/24. Okay. They are both reachable with the same next hop. So if you have a destination IP address in this network, you go through the next hop C. If you have a destination in this network, you go all the same through the same next hop. So it doesn't make difference in terms of forwarding. And also, these two blocks are adjacent. Okay, the first one starts, and the second starts when the first one finished, and they can be aggregated because this is a /24. Instead of writing /24, I can write here /23. This /23 matches with both of the blocks. So we can remove one of the entry and leave just one with the /23. It doesn't make any difference in terms of forwarding, but it decreases the size of the routing table. So each time you can apply root aggregation, you do it. Okay. And this is also a picture that shows you the pie chart. This is the whole network address block, and you can see here the first subnetting, which generates the two networks N1 and N2, and then here we have the second subnetting with N4 and N3, and then the subnetting of these slides. We generate the N5, N6, 7, 8, and then all the point-to-point links inside this very small slice. Okay. Yes.
In the example, should we put just R1, R2 in the next hop, or?
No, here you have to put the addresses.
So in the next hop, we should put the
IP addresses.
And for example, the IP addresses of R1 or R6 is?
You can choose anything. It's arbitrary.
Okay.
The important is that you select an address which is assignable to a host and which is included in the network. Okay. In this case, actually, the text specified that something that assign first addresses to all interfaces of routers R3 is connected to. So it means that in this case it tells you that here you have to assign the smallest assignable address of that network. Okay. So in this case the network was N5, so N5 started with 143.0. So you should assign here 143.1 to this interface. Okay. However, usually is arbitrary. The common practice is to assign the highest possible addresses to the router interfaces, but it's just a matter of decision. It's a convention. Okay. So now let's move to this other exercise. This is about TDM. Or TDMA actually. Multiple access system based on TDMA has a carrier rate of 4 megabit per second, and it is used to transmit N data channels with each with a rate of 200 kilobit per second. This is the rate of the tributary. Each slot requires 4 GAR bits. So it means that once I have the frame, I divide it into time slots, which are all of equal duration. But between the transmission of the bits into a time slot and the transmission of bits in the next time slot, I must leave 4 bits for bit times of silence with no data. Okay? And this is to increase the robustness of the system towards, especially towards misalignments of the stations, or towards by considering the propagation time, as we have seen in the lecture. And the system is dimensioned for an efficiency of 90%. This means that the output channel of the multiplexer will be in transmission, so transmitting bits for 90% of the time. The rest, the 10% of the time it is not transmitting, is due to the GAR bands. to the guard bit. Okay. So the frame will be like this. We will have a time slot and then bits in each time slot, and then a silence for a time which is equivalent to 4 bits. Then again bits in the next time slot, silence, and so on and so forth. Okay. N is not specified, it's the number of channels, but the text asks to calculate the maximum number of channels that can be supported. And then after calculating the maximum number of channels, calculate the number of bits of the burst. It means the number of bits that are transmitted in each time slot. These bits here, you can call it the V. And then the duration of the frame and that of the slot. Okay, so this is the duration of the slot. Call it a time slot. Yes. The number of bits for of the guard band, we can call it G. And then we have n time slots, and this is a frame. T is the time of the total time duration of the frame. This is the multiplexer. There are n input lines. The rate on each tributary is given, and we can call it R. And this is the output rate W. Okay. So, first of all, we know that the rate W, that is the total rate of the output of the multiplexer, will be given by the rate that is consumed by the guard bits. Okay. This is practically a rate, because even if you don't transmit, you take a time. Okay. And then we have the rate that is needed in order to multiplex the n tributaries, which must be n times R. Okay, which is the rate of each tributary. This is the basic equation that you have to consider for the time domain multiplexer. So, since we know this, then what would be the maximum value of n? Obviously, n must be an integer number. Okay. So, if I want the maximum possible value of n, that is the number of tributaries, the maximum number of tributaries that are supported, I have to consider the ratio between W minus Wg and R, which is the rate of each tributary. And then we have to take the next smaller integer. Okay. Because this is, even if here we have max means maximum possible. So we have to take this ratio, and if the ratio is let's say 10 plus something, then the maximum possible number of tributaries supported is 10. Okay. So in this case we have we have also that the efficiency of the output, so the time that the output is always in transmission is 90%, and this is basically the ratio between well, let's call it that's the useful output rate divided by the total output rate, okay? And is exactly, the useful output rate is exactly what we have written there. So it's the total output rate minus the rate that is consumed by the guard bits, okay? And this is 90%. So here we can replace what we have written, and basically we can write that the Nmax is equal to the 90% or 0.9 of the ratio between W and R. Okay. Because this is equal to W by 90%. Do you agree? I see you a bit astonished. It's okay. Here we have, if you want, we can write it as the effective rate, okay, and the effective rate is equal to W by eta, which is 0.9 W. Okay, maybe now it's more clear. So, if we replace the numbers, here we have, I forgot to write the numbers, W is equal to 4 megabits per second. And the rate is equal to 200 kilobits per second. Okay. So this means that here we will have 0.9 4000 divided by 200, which is 20. So we have 0.9 by 20, and it is exactly an integer number, that is 18. Okay. Okay. So the maximum number of users that can be hosted, or tributaries that can be accommodated, is 18. Sorry, maybe I date. Now we have to refer to this number in order to do the rest of the exercise. And the question is, what is the number of bits in the burst? And so here we know that the total duration of the frame T, it will be equal to 18, which is the number of slots. Right. So, Nmax, and then each slot contains So this is nmax by ts, is the duration of the slot. Now each slot contains B bits that are transmitted, taken from the tributaries, and G bits that are simply transmitted as silence, okay, because they are the guard bits. So here I can write down that the duration of the slot is equal to B plus G, and we are transmitting everything at the output rate, which is W, okay? Then here we have T that is unknown, B is unknown, the rest is known. So we have two unknowns, we need another information, and the other information is that in the duration of the frame, each tributary must produce exactly B bits. Okay? So T frame is also equal to B divided by the rate of the tributary. Okay? Otherwise you have a mismatching, you cannot transmit all the bits. So we can put these two equations together, and then here you have that B divided by R is equal to nmax B plus G divided by W, and by this you can find the value of B. Okay, B will be equal to nmax divided by W by G RW divided by W minus nmax times R. Okay. It just comes from the solution of this equation as a function of B. This goes away, and then you have nmax is 18, we know it, G is known, is 4, R is known, and W is known. So if you solve this equation, you find that B will be equal to 36B. Okay. Of course, you have to solve a system, which is very easy. Well, so B is equal to 36 bits. Then once you have B, you can calculate both TS and T. And T, we say that it's B divided by R, so it will be 36 divided by 200 kilobit per second. So it will be 200 milliseconds. It will be 180 microseconds, if I'm not wrong. And then TS is T divided by nmax. That will be 10 microseconds. Okay. take it off. Questions? So the second part of the exercise, design a multi-frame system with a higher carrier rate, able to support, in addition to the NMAX at 200 kilobit per second, also NMAX signaling channels at 40 kilobit per second. Okay, this means that you will have to transmit the time slots carrying the data and the guard times, the guard bits. Plus, you have to dedicate some time slots to carry signaling channels. Okay, but if you look at the rate between so the signaling the ratio between the signaling channel and the frequency of each tributary, so we find that the signaling channel that is 40 kilobit per second is equal to R, which is the ratio of each tributary, which is 200 kilobit per second, is equal to R divided by 5. Okay, so the signaling channels are 5 times slower than the tributaries. So when you have this situation, we can build a multi-frame structure. This means that we will have 5 frames dedicated to the transmission of the data, plus 1 frame for signaling. Okay. This is a sequence of frames, so the transmitter actually, we draw it this way, but the transmitter will transmit everything serially. So it starts from the first frame, then transmits the second, then transmits the third, and so on. And then transmits the signaling frame. And in the signaling frame, the number of slots that you have is exactly equal to the number of slots that you have in each data frame. Okay. And here, if we assume that we still keep the NMAX equal 18 that we calculated in the first part of the exercise, the number of slots will be always 18 in all the frames. But if you transmit 5 frames of data and then 1 frame of signaling, then you are satisfying the requirement of transmitting a signaling channel which is 5 times slower than the frame, the tributary frequency, one signaling channel for each tributary. Okay. So the total number of frames in the multi-frame structure, let's call it NMF, will be equal to 6 because we have 6 frames in all. And the question is, what is what are the number of frames in the multi-frame? So that the answer is 6, and we have to calculate the multi-frame duration. Okay. So here we don't know what is the output, the output rate of the multiplexer, because here it says that the carrier rate is higher, so we will have a W prime rate, which is unknown. But we know the rate of the tributaries, and also we know the data structure of the frames. And here also the text specifies that we have to keep a constant the number of slots per frame and the number of bits per slot, which is the same calculated in the previous exercise. Okay, so we still have b bits per slot, where b is equal to 36, and g bits of guard time, which is equal to 4. Now we want to calculate the total duration of the frame, of the multi-frame, and so we know that in a time of the multi-frame, what is the amount of data that is produced by each tributary? Okay, so the amount of data will be equal to n frame, n multi-frame, minus 1, because we have 5 frames of data, multiplied by b, which is the number of bits in each slot. Because in each frame, each tributary has one time slot. In each time slot, each tributary will produce b bits, and in a multi-frame time, each tributary will produce b bits and nf minus 1 times. Okay, so 5 times basically. And this is the number of bits that is produced by each tributary, and we know that the tributary produce these bits at the rate that is r, which is known. Okay, so the time of the multi-frame should be equal to 5 times b divided by r. If you translate it into numbers, we have 5 by 36 divided by 200 milliseconds, which is 900 microseconds. Okay, so this is the total time of the multi-frame. From the total time of the multi-frame, we can calculate the total time of a single frame, which is T mf divided by n mf, which is 900 divided by 6, 150 microseconds. Okay. The last question is the carrier rate. Okay, so we have the duration of a single frame. What would be the carrier rate? And here it's very simple, because now we know how much is a frame, and we know that in each frame we have the transmission of n max time slots, and each time slot contains b bits plus g guard bits. Okay, and this is divided by w prime, which is the new rate of the multiplexer, output rate of the multiplexer. So immediately we can calculate what is w prime. That will be equal to n max b plus g divided by t. And if you do this calculation, it should be 4.8 megabit per second. Okay. So this exercise was not easy at all, but it's good to make it for practice. Okay, questions? Now let's move to the final numerical exercise. So in the network shown below, host A establishes a TCP connection with host B. Then we can assume that the header and arc lengths are negligible, links are bidirectional, the maximum segment size is 1000 bytes, receive window is 17,000 bytes, slow start threshold is 8,000 bytes, and so we have to calculate the time necessary to transfer a file of 50 kilobytes from A to B. From the time the TCP connection has been from the setup of the TCP connection to the reception of the last ACK packet. And here we have a network which is composed by a host interconnected to the final host through a router. And the two links are 1 and 2. So the first link is in case 1. Okay. The first link is operating as at 2 megabits per second, the second at 4 megabits per second, and both propagation times are 100 milliseconds. Okay. Then we have to replicate in case the propagation times are shorter. So here we have a TCP connection, and first we can start also calculating all the data regarding the management of the congestion window in terms of maximum segment sizes. So for example, the receive window that is 16, the maximum segment size, first of all, is 1000 bytes. Okay. The receive window will be equal to 16,000 bytes, so it means 16 maximum segment size. Slow start threshold is equal to 8,000 bytes, so it means 8 maximum segment size. Okay. These are the initial conditions. The receive window remains constant for all the connections, so that is basically what we can assume from the text. And as you know, receive window is always the boundary for the transmission window. The transmission window, we always take a value which is the minimum between the congestion window and the receive window. Then we have also the size of the file, which is 50 kilobytes. And kilobytes, it means 1000 bytes. And so this is equivalent to 50 times the maximum segment size. Okay. This is the preliminary conversion you always have to do in this kind of exercises, because all the variables of the congestion window are always normalized to the maximum segment size. Okay, so now we have to calculate what is the transfer time, and the first thing to do is also to compute the transmission times. Here we can assume that each packet contains exactly number of bytes that is equal to the maximum segment size, because the text says that all the overheads, the headers are negligible. Okay. So since the packet contains maximum segment size, the transmission time of the packet out of the interface of A towards R will be equal to MSS divided by C1, which is the rate of the first link, you always have to remember to multiply by 8 because the rates are always in bit per second and the maximum segment size is in byte. So it's 8 by 1000 divided by 2 megabit per second. So it's 2000 kilobit per second, which translates into milliseconds. Return, I put it on the denominator. This means that transmission time is 4 milliseconds. Okay. T2, always NSS divided by C2. C2 is twice C1, so the transmission time will be half, so it will be 2 milliseconds. Okay. Now, we have to understand what happens when we are opening the connection and then starting to send the TCP segments. If you remember, in TCP we have the three handshake phase to open the connection. So it means that the first connection is opened by A towards B. Okay. So the first packet that is sent from A to B contains only a header. The first segment contains only a header, no data. And as the text says, in this case, the length is negligible. Okay, so it has a transmission time equal to 0. So it is generated at a certain time, which is 0 times 0. And then we have the propagation time towards the router. In the router, it is received instantaneously because it has no duration and immediately retransmitted. And we have another propagation time towards B. So you can notice that in this case, tau 1 is equal to tau 2, and it's 100 milliseconds. Okay? So basically you can show in the time diagram this first packet by drawing a straight line towards the destination. And then we have the reply of B, which is again only a control packet. It contains no data because data can be started to be transmitted only with the third segment. Okay. So this will be the one with SYN and ACK that are flags that are set, and then you have the return segment. And then A can start sending data, okay, from this point. So here, from here to the reception of the reply from B, we have a first time, I call it round trip time prime, which is because now we will have another round trip time which is different from this. Okay. So what happens when A can start sending data? We are at the beginning of the TCP connection. So at the beginning of the TCP connection, the congestion window is initially set to 1, which means that according to the congestion window, the sender is allowed to send just one segment equal to maximum segment size. And since the congestion window is much lower than the receive window, is the congestion window that decides what is the size of the send window. Okay. So the sender is allowed to send one packet, too large. Okay. One segment, the segment propagates, so you have to consider in this case that you have a transmission time which is now not negligible anymore. We have data. You have a propagation time towards R. R receives the packet only when it is received fully, because we are always in the store and forward assumption. R can start retransmitting it towards B. Okay, so here we have another transmission time, which is the transmission time of the segment towards B, and then another propagation time. Okay. The transmission window is blocked to just one maximum segment size. So until the transmitter will receive the arc of this packet, it will not transmit anything else. Okay. When B has received correctly the first packet, it will send the arc. And again, the arc, as the assumptions that are stated there, is of negligible size, so we can draw a straight line towards the source, towards A. Okay? Now, only when A receives this arc, then it can start transmitting again. And this interval, we can call it round trip time, without prime, because it's different from this one. Okay? Because here you have the transmission times from A towards B. Then what happens when B receives this arc? We have the slow start behavior of the congestion control. Okay? Because the slow start threshold is 8 MSS, congestion window is 1 MSS, so it's much slower than the slow start threshold, much lower. And therefore we are in the slow start phase. This means that we have transmitted one segment, we receive the arc of that segment, we can transmit 2 segments. Okay? Then these segments propagate. This is the first one. Notice that in R, when the 2 segments arrive into R, here we don't have any queuing delay, because the transmission time in R, T2, is 2 milliseconds, while the transmission time of T1 is 4 milliseconds. So here we don't have that the second packet has to wait to queue for the first one. Okay? And this is nice because it simplifies the problem. So when then A receives back the second arc, then it can start transmitting again. And it is always basically it is okay, it should wait for the second arc to transmit to be able to expand the window. Okay, but the second arc will come just after. Sorry, I am outside. The second arc will arrive just after the first segment is transmitted. So basically, it is not perturbating the behavior of the window. Okay. So since we receive 2 arcs here, now the A is allowed to transmit 4 packets, and so on. So the question is, will be, if we have this behavior, basically you can understand that now everything is timed by this RTT. Okay, this round trip time. Each time we have a round trip time, we have the transmission, an event of transmission of new segments. The question that we have to ask is, would it ever be possible that at a certain time we arrive to a window size that is saturating the round trip time? So it means that at a certain time, if we arrive to this situation, here we have the round trip time, and A is allowed to transmit packets until the end of the round trip time, then it means that this window will start sliding even before we get all the acknowledgements of the other packets, and so you will have a continuous transmission. So we have to check if this situation of continuous transmission will ever be possible in this case. But in this case, what we have is that the receive window is 16 maximum segment sizes. So it means that the transmission window will never be greater than this, no matter of how you increase the congestion window. The transmission window is bounded by the receive window. And in this case, when we have 16 MXS, what happens? So let's consider that the round trip time is equal to T1, the transmission of the first maximum segment size, plus tau 1 plus T2 plus tau 2 plus again time tau 1 plus tau 2. Okay. And since all the propagation times are given, we can translate it into a number. This is 1, 2, 3, 4 times 100 milliseconds plus 4 milliseconds plus 2 milliseconds. So it will be 406 milliseconds. Okay. This number, this value is much greater than receive window divided by MSS, of course, multiplied by T1. Okay, because this is receive window divided by MSS is equal to 16. T1 is 4 milliseconds. Okay, so you can see that round trip time will always be larger than this value here. So it means that in this case you will never have the continuous transmission. So once we have checked this condition, we can also consider this graph, where here we have the time normalized to the round trip time, and here we have the send window. Okay. And so we can analyze the behavior of the send window by using this method, which is simplified. This is 1, 2, 3, 4, 5, 6, 7. Okay, and receive window is up there on the top, and then here we have the slow start threshold. Okay, then if we fixed here, say, the round trip time, time 0 at this moment, okay, when we start sending data, the congestion window is 1, and also the send window will be 1, okay? Then, after a round trip time, congestion window will be 2, equal to the send window. Then we have another round trip time that we have received we have received 2 acts and sent 2 packets, so we can increase by 2. So we have a congestion window equal to 4. Then we will go to 8. Okay, the next round trip time. When we arrive to congestion window equal to 8, we are outside, we are at the boundary between slow start and congestion avoidance. So it means that in the next round trip time, the window will be 8 plus 1, so 9, because I have to increase the window by 1 divided by the number of acts received, the size of the window, multiplied by the number of acts received. So if you remember, this is equivalent to a linear expansion of the congestion window. So in the next time slot we will be at 10, then at 11, more or less here, okay. Okay, this is this point. We have also to check how many bytes of the file that we have to send has been sent. Okay, because sooner or later we will run out of the bytes. So we have, I write here the count of the transmitted bytes of the transmitted maximum segment size in, say, the bottom. I don't know if you, maybe you can write it here on the top. Okay. So here we transmitted 1, then it's 3, then here it's 7, then it's 15. Here we have 15 plus 9 is 24. 24 plus 10, 34. 34 plus 11 is 45. Okay. So now in the next round trip time, the congestion window will increase again, but we have only 5 segments to send because we are running out. So the transmission, the actual transmission will be here. Okay. So this is the first round trip time, second, 3, 4, 5, 6, and 7. Okay. You can use this scheme, which simplifies a lot the analysis, because we have checked that everything is clocked to the round trip time. Okay. So, what is the total time in this first case? Total time will be equal to, first we have the opening phase, so it's this round trip time prime, and then we have 1, 2, 3, 4, 5, 6, 7 round trip times. So the first one okay, and then we have the transmission, so we have 1, 2, 3, 4, 5, 6, seven round trip time, plus then we have the transmission of the final five segments. The final 5 segments will be transmitted one after the other because the window is open, and so it's large enough, the transmission window. And then we have to consider when the last ACK is going back to A. So here we have to take the last segment and then calculate the time that it takes for the ACK to get back. Okay. So then we have to, actually there are 5 segments. 1, 2, 3, 4 segments. This is T1, actually 5 segments, so 5 times T1, plus we have T2, plus 2 times tau1 plus tau2. Okay. So this should be the final transfer, the total transfer time of the 5. And this first RTT prime is 400 milliseconds. Seven times 406. Then we have 5 by 4 milliseconds. Oh, wait. That's 4. Then we have 2 milliseconds. And then we have again 200 milliseconds. Okay. I don't know what is the final number. So this is the first case. Then we have the second case, which is point number B. So in this case, we have to consider that the propagation times are shorter, propagation delays are shorter. So it may happen that you have continuous transmission. Okay.
Excuse me?
Yes.
So in TCP we start transmitting the next group after receiving the first ACK?
Actually, it's not like that. You start transmitting you start transmitting the next group after receiving the first ACK. But while you are transmitting, the other ACKs counts. So when you are considering the graph that I showed you below, basically you are simplifying things by assuming that all ACKs arrive at the same time and all packets are transmitted at the same time. In some cases you can do it, because, for example, in the case that we saw before, it's not always possible. You have to be careful, but when it is possible, the graph that was below allows you to do all the analysis of the congestion window in a simplified way. Okay. So now we are in a different case. So here we have that tau 1 is equal to 10, tau 2 is equal to 6 milliseconds, T1 is always equal to 4 milliseconds, T2 is always equal to 2 milliseconds. Okay. So, in the opening phase, we have this situation. We have first propagation time, which is larger than the second, and the durations of the segments are negligible. What happens then in the next, when we start transmitting data? This is the first segment. More or less. We have to check again if we have the condition when we have continuous transmission. This time the propagation times are much shorter than transmission than before. So the round trip time, which is this interval here, round trip time in this case is 4 plus 2 plus 2 times 10 plus 6. This is T1, T2, and 2 times tau 1 plus tau 2 milliseconds, which is equal to, this is 16, 32, 32, 36, 24, 38. Is it correct?
Yes.
I did a mistake in my solutions. So 38, and so if we consider round trip time divided by T1, which is transmission time, it is 38 divided by 4.
9.5.
So 9.5 means that when the congestion window is equal to when the transmission window is equal to 9, we have continuous transmission. Okay.
It's not only right to 10 has to be. 9.5 means I still have a small to do before it becomes continuous.
When
it's 9, he has to do 9.5 to become continuous. And so I have to do is still do a bit. So when it's 10, it became continuous.
when it's 10, because when it's 9, no, because if it is 9, yes, must be 10. Yes, must be 10. When it is 10, we have continuous transmission. Okay, so when the send window is less than 10, basically we are in the same conditions as in the previous case. When it becomes 10, then we have the continuous transmission. Now I have to draw something that is smaller, otherwise I cannot stay this. So here we start with the opening phase. Now I draw a simplified view. Then we have the first, then we have this is RTP. Okay. Second is with sending two segments, then we send 4 segments, then we send 8, then we send 9, this is 1. This is the congestion window. Then we have the transition to the congestion avoidance. So here we are transmitting 9, and then here the window is 10, and now the transmission becomes continuous. Okay, so the transmitted data is in maximum segment size. transferred. Here we have 1, 3, 7, 15, 15, 24, and then in this, at this moment we have transmitted 34 segments. Okay, so we have still other 50 minus 34 is 16 segments to send. Okay, so here we will transmit other 16 segments, and this would be the last one. Okay. Then when we send the last one, here we will have transmission of the intermediate packet, and then back reacts. So in this case, the time, the total transfer time, will be given by RTT prime plus 1, 2, 3, 4, 5, 6 RTT plus then actually we have to consider that the last RTT is not exactly finishing with the transmission of the last packet. So it's better to write here 5 RTT, it is 1, 2, 3, 4, 5, and then from here we have continuous transmission basically. So we can start from this time here. Here we are transmitting 10 MSS, okay, and then instead of considering 16, here we can consider other 15 MSS, and then from this time, including also the last MSS that is transmitted until the reception of the last ACK, we have another RTT. Okay. So here we can write 10 plus 15 T1 plus a final RTT. Okay. So this is the total transfer time that is different from the one before. I don't have the numbers, the final number, but you can easily calculate. Okay. It's very late. Very quickly, this exercise is about distance vectors, and okay, let's do it faster. You can see here there is this topology, and the first question is write the content of the distance vectors sent by R3, R4, assuming a split horizon with Poisson reverse. And this is actually one of the theoretical questions, which are actually in this case is a small exercise. So first of all, you have to write the routing table of R3, and the routing table of R3 has to be written considering the topology, and in red you see the minimum path 3 towards, sorry, in this case it's not it's R4. I wrote R2, but actually it's R4. It's from R4. So you can see here the routing table between R4, over R4, which is built by considering the minimum path 3 from R4 to all the other destinations. In this case, destinations are the routers. And it's the red line. It's written R2, but actually it's R4. So this is the resulting routing table. For example, R1 is seen as at a distance of 2 using R2 as a next stop. Okay, R2 is at the distance of 1 using R2 as a next stop, and R3 and R5 all are reachable from R5 at the distance of 2 and 1, and R4 obviously is at the distance of 0. So R4 sends the distance vectors to its neighbors and only to its neighbors, and it will, since we are assuming split horizon with Poisson reverse, it will indicate a destination in the distance vector with a distance infinity if the next stop is the node where it is sending the distance vector. For example, when R4 is sending the distance vector of R2, this is the list of the destinations, but since R2 is appearing as a next hop for the first 2 items, the first 2 distances are propagated as infinity. Okay. The same for R5, which appears as next hop for R3 and R5, and R3 does not appear as a next hop, so all the distances are propagated as they are. Okay. And then the second part of the exercise is to repeat the exercise using R3 as the originating node. So you have to again build the routing table of R3. In green you have the minimum path 3 originated in R3. So all the destinations are connected by R5. And so the next stop is only R5. So you can see that when the distance vector is sent to R2 and R4, all the distances are as they are in the routing table. When it is sent to R5, all the distances are infinity because except R3, which should be a 0 and not a line. Okay, so this is very simple as an exercise. And then this is the last exercise that you can do. Actually, there is another question, but it's on fast retransmit as fast recovery. We don't have seen that specific topic in the course, so you can leave it out. Instead, this is about forwarding. You have a routing table, which is this one. This is the routing table of a router, and you have also the interfaces, all the interfaces with their IP addresses and netmask, and the entries of the routing table with IP address and netmask, next hop indication. And then you have a list of packets that are arriving to the router, and you have to understand how the router is forwarding each of the packets. Okay. So for example, if you take the first packet has this IP address. That IP address is matching with one of the interfaces, with interface ATH0. So it means that forwarding will be directed, but you can see that here in this packet you have a size of 600 bytes, and D is the flag do not fragment. The flag is set to 1, and if you look at the interface, the maximum MTU is only 500 bytes. So since the size of the packet is overcoming the maximum MTU and the packet has the flag do not fragment, the packet is dropped. Okay. Then you have well, another example is the second one. This is not matching with any of the interfaces. This is the IP address of the destination. It's matching with row 4 of the routing table, so you have to do indirect forwarding. Size is 500 bytes, and there is the bit, the flag do not fragment that is set. The next stop that is corresponding to the matching entry is this one. This next stop is connected to interface ATH0. ATH0 has an MTU that is 400 bytes. The packet is only, 500 bytes. Okay, and the packet is exactly 500 bytes, so you can send the packet. You also hear the time to leave. In this case, is 2. So when you decrement it, it's 1. So the packet is still alive, and so it can be forwarded. And just the last one. The last one is a direct forwarding through ATH1. The flag is not set, so you don't have to care about the size. But time to leave is 1, so when you are forwarding the packet to the interface, it is decremented, the packet has to be dropped. Okay. Okay, I think that's all. I will put on BIP the solutions of this exercise. For now, you have only the text. And well, if you have questions, write me an email and we can arrange an appointment if you have to discuss some issues. Okay, thank you.
Io avevo un po' di domande su alcuni esercizi.
Sì.
Non è possibile fare, cioè è possibile organizzare un complemento o il mando comunque un'email?
Mi mandi un'email perché diciamo che c'è anche in teoria il giorno di ricevimento, però dunque io non ci sono fino a mercoledì, sono in congresso. E
Ok.
dopo mercoledì
Ok, sì, vabbè, avrebbe bene lo stesso. Io mando un'email ogni caso.
Va bene.
Scusate per l'ignoranza, ma il vostro ufficio dove è collegato?
il
vostro ufficio dove
l'edificio 20, dipartimento
ok.
di elettronica.
Ok, ok.
Sì, dall'altra parte di questo via qua.
Ok, grazie.
especially where you have to